Yeah, I normally would have prepped stuff for the session this morning, but I got a phone call about a job offer, and that sort of took up most of my morning.
That's important, I imagine.
Yeah, I'm just gonna, yeah, sorry, Dr. G, I think that's slightly more important. But so, here, I'm gonna pull up screen share, pull up like the learning objectives and stuff. Um, are there any specific problems you had or you wanted to go over? Like either from like Flip It or from the discussion or anything? Or like any questions you have about whole ideas of work and energy and momentum? You guys haven't quite gotten into momentum yet, right? That's tomorrow's
Yeah, not
material.
yet.
The
Yeah.
centers of mass and work and energy. Any sort of general questions you have about it?
Um, I guess less so than questions. I'm just a bit kind of uh confused. I'm still a bit confused about the whole thing. I understand the general like the formulas and how I'm supposed to use them, but when it comes time to actually use them, I get really confused as to how I can manipulate them. Where's the problem?
Do you have a specific example? Is it from the discussion or from Flip It?
I was just looking at the discussion.
Okay, yeah.
Although I think I figured a lot of it out. Or I guess like I didn't really get to work on three. Like I basically just guessed on all of the problems because I ran out of time.
Oh, okay. So which problem do you want to go over? You want to
It's
start
the
with three?
problem with the pulley.
The pulley.
Yes.
The fourth problem or the fifth problem, question five.
Yes.
Okay, yeah. So sort of walk me through your process of how you'd approach this problem.
So when I was first approaching this problem, the first thing I did was I drew what are those called? Um, the diagram.
Yeah, free body diagram.
The three body diagrams. Yes.
Mm-hmm. So,
Of mass little m.
mm-hmm. Here, give me just a second. I what I like to do for like any problem I approach is I go through things step by step. Where first of all, I like to visualize what's going on, and for this case, I'm just going to steal the screenshot from the discussion instead of redrawing it myself in Paint with my mouse. Makes things just slightly easier. And so you mentioned you want to draw a free body diagram for little m. So let's go ahead and do that. So what are the forces acting on little m here?
We have the force of gravity acting downwards,
Exactly.
normal force acting at an angle,
Mm-hmm.
going towards the left.
Yep. And so if we like go ahead and draw a sort of perpendicular line here, where is this angle theta here with respect to?
Um, Theta would be um,
1, 2, or 3 here?
would be one.
Exactly. We have our angle theta here. So you can draw that. We have the normal force. Are there any other forces acting on little m?
The force of friction going to the left downwards along the dotted line,
Mm-hmm.
and then the force of tension going in the opposite direction.
Exactly. So we have friction and tension. So let me just label these. So we have the weight, we have the normal force, we have friction, we have tension. Anything else, or is that it?
I think that's it.
Mm-hmm. Okay. And what about big M?
Uh, Big M would have uh, three forces acting upon it.
What are the three forces?
The force of gravity, the force of going downwards,
Mm-hmm.
the force of tension going upwards, and then the normal force going downwards.
is there a normal force acting on M?
I guess it's not technically touching anything.
Yeah, it's not touching anything, so I would think it's just the tension and the weight.
Oh, that was a mistake I did.
Yeah, but that's pretty much it. So, give me just a second. So, the figure shows two blocks, M and M, connected by a massless rope. Block M is initially held at rest on a rough slope. The coefficient of kinetic friction between the slope and block M is mu k. M is released from rest and moves up the ramp a distance d and has a speed v after moving this distance d. Represent answers in the simplest terms of M, big M, mu, g, d, theta, v, and t, the tension in the rope. A lot of algebra going on in this problem.
Yeah.
This is the sort of thing. This almost feels like a problem that you'd see in like a 200 or 300 level physics class, where like you guys still at least occasionally see actual numbers, especially on your quizzes, because it's like automatically graded and you have to put in like the right answer within or like on Flip It you have to enter answers. Past 100 level classes in physics, you never see numbers ever again, except in lab classes. So
That sounds awful.
I mean, you just get used to doing algebra. Everything's in terms of letters and variables rather than numbers, because the reality is, at least theoretically, any monkey can plug numbers into a calculator at the end of a problem, but the monkey can't necessarily actually solve for the problem in terms of the variables. I don't know. It's just how physics people do it. So, first thing you want to know is, what is the work done by each individual force on M? So, what is work?
Work is the force over a distance.
Mm-hmm.
Force put on an object over a distance.
Exactly. So we have work is equal to the force on an object. Let me actually pull up the where is it? I think for some reason he has the equation sheet in the class 1 thing, but I always like to have the equation sheet pulled up. So we have work is equal to, well, it's the more general form is we have this integral of the force over a path dl. It's a line integral, but yeah, it's essentially, for most examples you'll see it's force times distance. So, but what conceptually is work? What does work do?
It moves an object.
Not necessarily just moves an object. The force moves the object, and the force does work. What happens to the object when work is done on it?
It gains energy.
Exactly. It gains energy. Specifically, what kind of energy?
If it's maybe mechanical energy.
Yeah, or in this, I think more specifically, kinetic energy. Essentially,
Oh, I guess.
the object is accelerated, work is done on it, it gains kinetic energy. It starts moving faster. Or if it's negative work, it starts moving slower, and it loses kinetic energy. This delta K is equal to the total net work done on an object. So that's what work is. So how would we actually calculate the work done by each individual force on M?
I guess my first instinct would be to relate all the forces that are acting on it.
So we want to relate all the forces acting on it. So, but this question is just asking about each individual force, right?
Oh, yeah.
So I would just keep it separately. We're just leaving it in terms of it's moved a distance d up the slope.
Oh, that's true.
So there's one force here where the work done on it would be 0.
Oh, that would be the normal force because it's perpendicular.
Exactly. So why does being perpendicular make the work done 0?
Because it has no effect on its motion. I think.
There's something in this formula here that you can use to explain it. What is this dot product here?
I'm sorry, I don't remember.
You've got the concept, you understand it. I'm just trying to see if you understand the math. But essentially, the dot product of two vectors is, so this dot product would be the magnitude of f times the magnitude of dl times,
Yeah.
times what?
Oh, I'm sorry.
It's the magnitudes times what? Something to do with the angle between them.
Oh, the angle would be 90, so it would be what would it be? It would be sine 90?
Cosine.
Oh, cosine 90,
Yeah, but
which is 0.
yeah, it's 0, so it disappears. So dot product is cosine, and cross products, which you'll see, I believe, this next week when we get into torques. It isn't really as much of a deal as it is in Physics 122, where you will learn to hate cross products. But cross products is sine. It's the same concept, magnitudes times sine. So, obviously for normal force, dot product 90 degrees is 0. What about the tension? How much work does the tension do on M?
Um, for this problem, so it says that the term T represents tension, but that wouldn't be like tension given. That would just be like when we're calculating, right?
Well, we're just leaving it in terms. We're not actually like calculating numbers here. We're just, because you see here how it's giving us, essentially we're representing answers in terms of the masses, friction, gravity, the distance, the angle, velocity, and the tension. So we don't have to worry about solving for the tension. We're just saying, oh, there's a tension T. How much work is being done by it?
Okay, so the work done by tension would be the tension times the distance.
Exactly. It's just force times distance, because dot product cosine of 0 is just 1. It's just TD. Boom. It's that easy. Now, what about the frictional force?
The frictional force would be the K times mgd. Wait,
Almost. How about leave it in terms of the frictional force, just in terms of F, the frictional force. So what is the work done by it?
that would be the friction force times the distance it travels.
Is there a positive or a negative sign in front of it?
There's a negative sign in front of the friction force.
Why is that?
Because it's going in the opposite direction
Exactly.
as the motion.
Yep. So now how do we represent the friction force in terms of what we're given?
Be negative mu k times the normal force times the, but then in this case the normal force would be 0.
Well, no, the normal force isn't 0. The normal force exists. It just doesn't do any work.
Oh, so the normal force would be mg mg cosine theta.
Yes, exactly.
D.
Exactly. It's just mg cosine theta. I had to like confirm for myself because this is the same angle theta here. And then it's cosine because adjacent over hypotenuse, mg is the hypotenuse. So we have negative mu k mg d cosine theta. That's the total work done by the frictional force. And it's in terms of mu k, g, m, d, and theta. So now how much work is being done by gravity?
Oh, for gravity, so the work done by gravity would be mgh, but in this case we don't have h, so h would be a d times, I think, d times sine of 30. I mean, sine of theta.
Yep, exactly. D times sine of theta, because h, if like, for example, this is the total distance d here, we have theta, and h would be d sine of theta. So, and is that positive or negative work?
This would be negative work.
Yep, exactly. Because we're like moving upward against gravity. See that it was negative mg d sine theta. That's all the work being done by all our forces on little m. Now, what about big M? What are our forces that are doing work on big M?
The two forces would be the force of gravity and the force of tension.
Mm-hmm.
For the force of tension, the tension along the rope is the same, so we could just put TD.
Mm-hmm. And is that positive or negative?
This would be negative because the block is moving downwards.
Yep, exactly. The block moving down, tension is upward. And then for the gravitational work, how much work's being done by gravity?
It would typically be mgh, but in this case, we don't know how far down the block goes, so we would have to replace h.
How do we get the distance the block moves? I mean, if this block slides up the ramp a distance d, wouldn't this block just move down a distance d? Because the rope's a constant length, right?
Yes.
At least,
that's true.
ideally, the rope is a constant length. It's not going to be like stretching or twisting or anything. So it's just mg times d. Is that positive or negative work?
It should be. That would be positive work.
Exactly. Because it's in the same direction as the force. The distance is in the same direction as the force. So now, third question, what is the change in energy delta E for little m? There are two ways to express it, either as delta K plus delta U, or as work NC. Provide both. So how do we find the total change in energy? This first thing, what is energy?
The two formulas we learned were delta E equals the kinetic energy plus it's called the potential energy.
Mm-hmm. Delta K plus delta U.
And then that's also equal to the non-conservative work done.
Yep. So we have W and C. So, first thing, let's do the delta K plus delta U part. How do we get the total change in kinetic energy?
So we would compare KF and KI.
What's the initial kinetic energy?
The initial kinetic energy should be 0.
Exactly. We're starting at rest. So, what's the final kinetic energy?
1/2 mv squared, and we're given v, so that would be as far as we could simplify it.
Yep, exactly. Is that the total mass, half mv squared? Is that the total mass, or is it just the mass of the one, or what is it?
That would be just mass little m.
Oh, right. This question is just asking for little m. So yeah, you're right. Half mv squared. And then, so that's the kinetic energy. What about the potential energy?
The potential energy would compare the initial minus the, the final minus the initial.
Mm-hmm.
So it wouldn't lose. I think it would gain potential energy as it goes up because it's getting higher and higher on the ramp.
Mm-hmm. So how much potential energy does it gain?
Uh, gain mg. Where's mg d sine theta?
Yep, exactly. It's the same it's mgh, and we found from earlier that it's just mg h, and then h is d sine theta. And that's pretty much it. I mean, that's our delta K plus delta U. Now, what about how do we get delta E as in terms of the non-conservative work?
Well, we would compare the two non-conservative forces, which would be in this case the tension and the friction force. Work. So we would just subtract them?
Yeah, pretty much. So which one do we want to define as positive?
For little m, T would be positive and the friction force would be negative.
Yeah, I like that definition because it's in the same direction we're moving. So we have the tension. What's the total work done by the tension?
TD.
Exactly. T times D. What's the total work done by the frictional force?
Negative mu mg d cosine theta.
Exactly. Negative mu k mg d cosine theta. Boom. That's the total change in energy for little m. Now, what about big M? It's the same thing.
For big M,
What's the total change in kinetic energy for big M?
kinetic energy would increase as it goes along. It just 1/2 big M. I'm guessing it would go at the same velocity as the other one, just in the opposite direction.
Yeah. Or I mean, it's the same. It's the same speed. Um, I mean, because obviously the rope is still attaching them, and the rope's still at constant length. So yeah, just half big M v squared. And what's the total change in potential energy for our big M? The first thing is the total change in potential energy going to be positive or negative? Are we gaining or losing potential energy?
I'm sorry, what did you say? My
Oh. Oh.
Hello?
Yep. I hear you. That was weird. It was like you were quiet for a second, and then you were like, all right, sorry, what was that? And what did you say? My connection. And then you just dropped. But so what's the total change in potential energy for big M?
Oh, for big M, its change would be negative MGD.
Mm-hmm. Yeah, exactly. It's just MGH, and we know it's going to be negative because it's going down. H is just D. Sorry, big M, G, D. So now, how do we find the total change in energy and how do we find it in terms of the total non-conservative work?
So this would be, where is it? Just WG minus WT.
Mm-hmm.
So I would do the same thing. MGD minus TD
Yep.
minus negative.
Minus TD. And we're saying it's negative. Just, I mean, the negative is already part of it, and we're just adding the total non-conservative work together. So yeah, it's just MGD minus TD. So we found the total change in energy for both little m and big M in terms of both the total non-conservative work as well as delta K plus delta U. So how can we use all that stuff to determine the final speed of the blocks? We actually I want to see if I can pull up the solutions just to make sure we're going the right direction as to what they want us to do. I'm like 90% sure.
It seems a lot harder yesterday. It doesn't seem as complicated now.
See work, discussion solutions. I'm pulling this off to my other monitor so you can't peek. Oh, there's one thing we accidentally forgot to do here. We're pretty much completely right, except for one thing here with big M. Which of our forces acting on M are conservative and which are non-conservative?
The force of tension and the force of gravity would be non-conservative.
Is gravity non-conservative?
Is gravity the one that's always conservative?
Yes, gravity is always conservative. So wait, have we done this wrong for... No, we did it right for little m. We did it wrong for big M. Essentially, it's literally just minus TD.
Okay.
Apart from that, I think we're pretty much on the right track. Let me just double check. for little m. Oh, I think their solutions are actually wrong. That's funny. Yeah, the solutions on the discussion are wrong. But so anyway, we found all our different changes of energy based on both the non-conservative work as well as the delta K plus delta U. So how can we find the final speed of the blocks? I guess the first thing we want to know, what are we trying to find?
The final velocity.
Exactly. We're trying to find V. So what we want is V. How can we find V in terms of other variables we already have? That is our goal. So let's write down all our equations here that involve V.
We could use the kinetic and the kinetic energy equation, and then the kinetic potential energy.
Yep. I mean, I'd say this right here would be a good starting point, where we have our delta E for big M. We can write it in terms of half mv squared minus mgd, or minus td. And we know that those are going to be equal to one another, right? So we can just equate them. So we have half big M v squared minus big M gd is equal to minus td. So then half mv squared is equal to mg d minus td, right? And then
yes,
we can just solve for v. So we have v squared is equal to 2d mg minus t over big M, and then we just square root. And we have our velocity. Square root of 2d big M g minus t over big M. What variables are we given?
It's the last line of the problem. Does all of the variables.
So which variables? So we're given. I'm just trying to figure out. So this, I don't think this is our final answer here, because we probably also want to find the tension.
Oh, we're given m mu g d theta v and t.
I know this is a weirdly worded question, but I think this might just be our final answer. We don't even need little m, but we could use little m to eliminate the tension, I believe. I'm not sure. I'm not sure. I'm looking at the solutions, and the solutions are a mess and appear to be wrong. Unless I am now retroactively failing Physics 121, even though I have a bachelor's degree in physics. I do not blame you for getting confused in discussion yesterday, because these solutions are not helpful. But I think this is pretty much it. I think we're pretty much good here. We've solved
Yeah,
for
this
the...
makes a lot of sense.
Yeah, like this makes sense. We've gone through the math everywhere. I'm not sure what else they would want us to do. I guess we could also solve for v in from the little m. We could set both of these. We could set both of these equal to one another and solve for v that way, if we wanted to. But I like this. This is nice and easy and doesn't have a bunch of angles and stuff.
Yeah, this looks prettier, if you imagine.
So do you have any questions about this?
No, it makes a lot of sense now, actually. Thank you.
Yep. Anything else you wanted to go over? Because I feel like... Wait. Oh, I see also the order of the questions. 3... Oh, okay, yeah. The order of the questions and the solutions are weird. Yeah, question 4 on the solutions is question 2 from the actual discussion. Question 5 from the actual discussion is question 3 on the solutions. God, this thing's a mess. Do you have any other problems you want to go over?
Let me see.
We got about 15 more minutes here.
Is this the same? Oh, this is discussion 6. I think at the moment, that was the only question I had because just setting up all of those equations has been really tripping me up. Like, I think on discussion day, my group spent like most of the time just doing the first problem because we couldn't figure it out.
Do you want to go over that first problem, or are you pretty confident with it? Let's see, mass is pulled up a horizontal floor with no friction. Distance to stimulus, then the mass is pulled up an incline that makes an angle theta. There's the horizontal and the coefficient of friction. Mass's rope is used to pull blocks pulled parallel to the incline at an angle of 30 degrees. This incline is parallel to the surface. Tension 50 newtons. Okay. Interesting problem. So, what gave you trouble on this problem?
Oh, I just didn't know how to set it up, but I think that with
So, how would you set it up now? Take me through it one more time. Yeah.
So for part 1, I think what we ended up doing that was that it was easier setting it up looking at the work that was done instead of looking at we started with doing the kinematic equations. I think it was a mistake.
Oh boy, yeah.
Um,
Conservation of energy and work simplifies things a lot. Go ahead.
Yeah. Oh, so we started off with the energy. So the change in energy initial would be the same as the final energy.
Mm-hmm.
And so since it starts at rest, we know that the kinetic energy, the initial kinetic energy would be 0.
Yep. What about the change? What about the potential energy?
The potential energy, I think, wouldn't change because it doesn't like go up and it doesn't change its height.
Yeah, exactly. There's no change in potential energy, so the total change in energy is just the change in kinetic energy. which is equal to what?
That would be 1/2 mv squared.
Yep, exactly. So we have half mv squared. And so that's the total change in energy. How else can we write the total change in energy? That was the delta E is equal to delta K plus delta U.
Oh, yeah.
So we can also write it in terms of the total non-conservative work, right?
Yes.
So what is the total non-conservative work done on the block?
Total non-conservative work would be T minus friction, but there's no friction, so it would just be the tension.
Mm-hmm.
Which is pulled at an angle.
So what's the work done by the tension?
T, what is this? T cosine 30?
Yep. And then times what?
Times the distance traveled should be 10.
Exactly. It's just TD cosine theta. So then we just have to solve for velocity, and we're given the mass, we're given the tension, we're given the distance, we're given theta, and it's just solve for the velocity. So then how far up the incline does the block travel before coming to rest? Wait, then the mass is pulled up. That's how the mass verb is used. Parallel. Oh, okay, I see. So how far up the incline does the block travel before coming to rest? How do we solve for that?
This one is this one is rough. So we would use that equation, the delta K plus delta UG equals W and C.
Mm-hmm.
We can find the non-conservative forces pretty easily because we already know the tension, and because it's going parallel to the surface, it would just be the full tension instead of just T times
Cosine.
an angle.
Yep. So we know that the total non-conservative, and let me just zoom back in. So we know that W and C is equal to T times our distance. We'll call it X. T times X. And then, are there any other non-conservative forces here?
We have friction here as well, so it would be the force of friction times normal times the distance traveled, which would be X in this case.
Mm-hmm. So mu K X times the normal force. What's the normal force acting on our block on the incline?
A normal force would be perpendicular, so
Mm-hmm.
0? Or I guess it wouldn't be 0 for next. It would be mg times cosine 30.
Mg times cosine of 30. Same thing as before up here. You're exactly right. Mu K mg cosine of 30, or theta. I'm just going to leave it in terms of theta. So that's the total non-conservative work. And then we write that is equal to delta K plus delta U. What's the total change in kinetic energy?
Total change in kinetic. The kinetic energy wouldn't change because it's being pulled at a constant speed.
How would it be pulled at a constant speed if we're eventually coming to rest?
Oh, my bad. So the kinetic energy would start off as 1 times mv squared and would end up at 0.
Yep, so the total change would be negative half mv squared. What about the total change in potential energy?
The potential energy would grow as it um, goes along the incline, so it would be positive mgh. And I guess if we regard as like the bottom of the incline as being 0, then we could eliminate the initial.
Mm-hmm. Sure thing. And so what would our total height traveled upward be?
Well, total height would be x times sine of 30, sine of theta.
Exactly. Just x times sine of theta. mg x times sine theta. Is this everything we need to find x?
I think so. We could just put them equal to each other.
Yep. And then we just do a bunch of algebra. So we have... Well, what I'm going to do is I'm going to move this to the other side of the equation. So I'll write everything. I'll have x times, in parentheses, tension here, minus mu k mg cosine theta, minus mg sine theta, is equal to negative half mv squared. So then we just have x is equal to mv squared, 1/2 over all this stuff with the negative sign, and it's like t minus all this stuff here. And then we just solve for it, right? Because we know the mass, we know the velocity from the first part, we know the tension, we know mu k, mass, and we know the theta. And we could plug in and solve with numbers, but like I said earlier, the main brunt of the work has been done. Any monkey can plug stuff into a calculator at the end.
Yes.
Though, unfortunately, you monkeys are actually graded on that ability on your quizzes, so sort of unfortunate.
Yep.
Yeah, that's it. Do you have any other questions about this stuff?
No, I think I understand it a lot better now.
Okay.
Thank you.
I might honestly just... the whole point of SI Pass is like I have my own like supplemental instruction sessions, but I feel like this was more productive than our normal things. Maybe I should be lazy and not prep things more often. Don't tell my boss.
I won't say anything. Oh my god, the discussion was awful. I actually didn't know what I was doing.
Yeah. I feel that's definitely, I think that's that's the thing that's really suffered the most with the online format is I feel like students being together in person, working together on things makes things work so much better. And being online, you have people just have low effort and energy and they don't want to do things, or they don't feel as it just doesn't work as well. Because like
It's a struggle.
anyone can watch flip it video pre-lectures and attend lectures and do practice problems and clicker questions and online lectures. It's pretty much the same as in person. It's just you're sitting at your computer instead of being in a large lecture hall, but the discussions is really where things suffer. All right, well, that's gonna pretty much be it. I think I'm gonna go ahead and wrap up our little session here. Hope this helped out, and good luck on the quiz tomorrow, and good luck working on the stuff as we move into stuff like momentum and conservation of momentum in the next week.
Thank you.
Still find it weird that we do energy before momentum, but that might just be because I did momentum first before energy back in high school. All right, bye. Thanks for coming.
Um,